Our next flashback video will be about solving systems using elimination. So, just like we started with substitution, we can use elimination really for any problem, but there's a certain way problems appear that makes elimination the best choice. And when I use elimination is when I notice that both equations are in standard form. Just as a reminder, just in case we forgot, standard form means that both variables are on the same side of the equation. A variable is already, especially usually if we talk about graphing y, is not isolated. So that's when I use elimination. So we're going to take a look at 3 word problems where we would use elimination. In the last video, I know I went through a couple of the last problems pretty quickly. If you feel comfortable after I've set up the equations, feel free to go ahead and pause, solve the problem, and then play it through so you can see what we did, just so that you understand. In my first problem, it's one of those classic, brain teaser types of questions. So it says find the value of 2 numbers if their sum is 10 and their difference is 6. Just to kind of make sure we remember our vocabulary, it's a little bit flashback. Sum means addition, difference means subtraction. Now it's our choice to determine the variables, and really I should have included that as step 1. Because we don't really have anything super specific about the variables, I just kept it pretty classic. And I just said that x plus y is 10 and x minus y is 6. By all means, you could reverse the order of y and x given another number, but since the word problem itself is just asking for the value of both numbers, it really doesn't matter. Now, eliminate means to cancel. And in elimination, we're looking to cancel out one of the variables. So in step 2, you want to look to see, could I eliminate a variable already? Now for elimination, we would combine these 2 equations, and that's why sometimes in some textbooks it's called linear combination. So if I were to add these 2 equations together, I notice that one of the variables would be eliminated, and that variable would be y. We have a positive y and we have a negative y, which means all canceled out. So I have a very happy yes. If you can cancel it out, we just combine the 2 equations. And it's as simple as adding them. Combine means to add. So when I plug this in, I come up with 2x is 16, x equals 8. So that means my bigger number is 8. Just like before, I want to take that number and plug it into one of the 2 equations. If I plug it into the first equation, I find out that y is 2. Just like in the last video, although I didn't type it up, I did check to make sure my numbers made sense. 8 plus 2 is 10, and 8 minus 2 is 6. So you always still want to go back. So hopefully this basic question gave you the idea of what elimination is. Now, although this problem we were like, woohoo, ready to go, we could eliminate a variable, the other 2 really don't have that luxury. So I just gave you not a word problem this time, but I did give you an example problem. And I just wanted you to think about, again, can you eliminate a variable already? Just looking at the 2 equations, I know my answer is no. I know it for 2 reasons. Number 1, both of the variables have exactly the same sign. These 2 are positive, these 2 are positive. In order for something to be eliminated, they need opposite signs. And I also can tell because these 2 numbers would also have to be the same. The absolute value of the numbers would be the same, and they're not. So if I can't eliminate a variable, it does add another step, but it's not too bad. My strategy when making something work is figuring out how to make one of them positive, one of them negative, and to have 2 numbers that match. Let me just show you what I chose to do. I usually choose to take care of the x, unless the y I can see a lot clearer. For this problem, I could set it up like this. I could also find something else to multiply these the 2 values by as well. Why I picked negative 3 is negative 3 times 5 was negative 15. Positive 5 times positive 3 is positive 15. A negative 15 and a positive 15 eliminate. Now you notice I did put parentheses around the whole equation. My careless mistake that I make is sometimes I forget to take that number in the front to the end number. So that's why I draw parentheses to remind me of what to distribute to. So in this next little set, you can see I multiplied every number in the problem by the number on the outside. So the first equation I multiplied every single digit by -3, and on the second equation I multiplied every single digit by +5. So then we combine, linear combination. What happens is my x's this time cancel out, and I'm left with 18y equals 72. Divide by 18, y is equal to 4. Now I can plug in 4 to one of the two equations. It really doesn't matter which one you choose. Not a big deal. If you notice, actually what I decided to do this time is just to show another way to check. I checked by plugging in 4 to both of them and seeing if I got the same answer. I just wanted to show you that it really doesn't matter which one you choose. You just choose whatever is the easiest for you to do or most convenient to do. I also did plug back x and y when I put them both back in, just to be sure I'm right. Now I only solved that on my calculator, and you're going to notice I start doing that a little bit more. Example 3. This is a classic example, and I put up there also another website. It's from kudasoftware.com. They have some great handouts with answer keys, and they include a lot of systems of equation word problems. Brenda's school is selling tickets to the spring musical. On the first day of ticket sales, the school sold 3 senior citizen tickets and 9 child tickets for a total of $75. The school took in $67 on the second day by selling 8 senior citizen tickets and 5 child tickets. What is the price of each of one senior citizen ticket and 1 child ticket? So just like in the substitution problems, before we do anything else, let's just make sure we know what's going to be our variables. And hopefully in the question you can tell. It's going to be senior citizen and child. So I just chose S and C. Now sometimes I don't choose S as a variable because my S's look like 5s, but since I'm typing this, I'm okay with using that. Now it should be really clear the equations you write because there's an equation for the first day and there's an equation for the second day. So for the first day I would write this equation, 3s plus 9c equals 75. On the second day, I would write that equation. Unfortunately, just like the second problem, I can't eliminate a variable easily just looking at the problem. Everything's positive, and that does happen a lot, especially when we're talking about money. Everything is positive, and none of the numbers are the same. So my answer is no. So I need to make it work. To make it work, we want to multiply. So this is a little bit smaller font, so in case you can't see it, I multiplied my first equation by -8, and I multiplied my second equation by +3. Let me try to zoom in a little bit on that for you a bit. So that's what I chose to do to find it. I simplified the two. And you notice if everything is positive, I'm always multiplying one equation by a negative number and one equation by a positive number. Have you noticed I'm always changing the first number? You have a lot of options, but for those of you who maybe struggle with this, this kind of sets it up to be a little bit clearer. So we go through, we solve, we make it work and combine. So I end up with -57c equals -399. So the cost of a child ticket, or C, is 7. So child tickets were $7. Next I want to plug in 7 to one of the two equations. So that would be what it would happen if I plugged it in to the second one. 8s plus 5c equals 67. I believe I picked that one first because I like to multiply by 5. Makes my life a little easier. But I also did, just to show you again another way to check. There are so many ways to check this. I hope you're seeing that the senior citizen ticket was 4. And when I went back in and I checked my work, it's exactly what I came up with. For your turn now, it's another example from Kuda Software. Let me zoom back out for just a second so you can see the problem fully. So here is the question very similar to the last question we did. Please solve it and we'll talk about it in class tomorrow.